All right, why don't we get started? It looks like we're about 10 to the hour, 12 to the hour. So you guys all set?
Yes.
All right, wonderful. Welcome to the MIDAS mini workshop on video coding. I am Jason Corso, and it's my pleasure to lead the workshop here. Just some protocol, I guess. There are more people coming, so we may break protocol with the next person or whatever. But if you do have clarification questions during the talks, please use the Q&A feature of Zoom to ask the question. But we'll have an open discussion at the end of the 90 minutes, and that should be good. So we have an exciting set of material to present to you today, mostly around the world of video. And you're probably aware, right? Like video is everywhere, from entertainment to defense to healthcare to education, even in like finance and banking. Like one can envision how video plays a role to some degree. You know, whenever we want to transform that raw signal into video, so into something we can process and model and do experimentation on or scientific analysis on, we need to engage in some form of video coding, right? So let's get a taste of what that is now. Hopefully my internet connection is fast enough that you can see this more than one frame per second. But video coding kind of asks questions about videos. Like if I asked you, and over Zoom in a webinar format, I can't actually ask you, but if I was to ask you what was happening in this video, you would say there's a woman playing the violin. Pretty straightforward. If I was to ask you what's happening in this video, it gets a little bit more complicated, right? Like, well, you probably know the movie, the scene where this is coming from. They're like walking through the Copacabana. So you have that context to help you understand what's happening in the video, but there's a lot of different people, a lot of different activities, a lot of different objects, probably even intent and so on. It gets pretty complicated. And maybe getting a little bit closer, talking about like understanding interaction between individuals and so on. If I was to ask you what's happening here in this video, probably you could all answer correctly, right? Like this is a kid's birthday party. Straightforward. But video coding wants to get more than that. What if I asked you instead, whose birthday party was it? Do you remember the image of the kid whose birthday party it was? Maybe in the middle there? Yeah, maybe that person. Right? So that's getting a little bit closer, a little bit more detailed in order to translate that video into something that we can analyze or annotate and process. If I asked you even more questions, which are getting a little bit more detailed in terms of what you might want to extract for actual analysis, you saw the video, then you saw the image. How many kids were at the party? Can you guess? This is much better in person, alas. Here's one frame from the video, and here's 1, 2, 3, 4, 5, 6, 7, 8. 8 kids. I think there's actually 9. I think if you kind of unroll it through over the course, there's one little kid who walks off scene. Right? So it gets pretty interesting and more challenging, even for us humans, when we see it once to do this type of analysis. But even a harder question: how old was the kid? Was the girl whose birthday it was? Can you even deduce what that answer is? 1, 2, 3, 1, 2, 3, 4, 5, maybe 5, maybe 6, based on the actual looks of the kids, right? So there was information there, but you had to pull it out, right? So video coding asks many questions about the video that we're looking at, so that we can translate or reduce the video into a measurable or quantitative nugget to do analysis on. Very concretely, video coding is not a simple classification problem. We're not only asking what is happening here, we're asking for real details about the video, whether or not we're doing it through human annotation or through automatic annotation or somewhere in the middle. Right? So it asks questions like what, who, where, when, even why in some scenarios, right? The role of in-video and world context is really critical and obvious in these scenarios. And as I began, right, video is everywhere. There are more than 48 billion cameras worldwide. YouTube alone gets more than 8 years worth of video uploaded every day. You probably could not even watch a small fraction of that video in the rest of your lifetime, or the rest of all of our collective lifetimes. There's just a lot of video in the world. How are we going to deal with it? Right? And the applications of video coding are wide, and we'll hear about two projects at Michigan today from my colleagues here, but there are also really interesting professional applications as well. So this is a video about a company in Canada called SportLogic that is used by, I think, nearly every NHL team and many college hockey teams to do analysis on things like technique, individualized technique, as well as team behavior, team interaction behavior. So they take raw input video from the games, they code information, analytical information about where all the players were, how many times you were on the ice when there was an assist, when there was a goal, things like that. Really fantastic level of video coding. And I think at this point, it's primarily automatic, but when they began, it was primarily manual. So there's a lot of interesting progress and stuff to talk about there. You know, at a low level, video coding is all about the representation, right? Both at a, like, if we're going to do it automatically, how should we pull information from the video? But then how do we think about representing that information we pull from the video into something that is crunchable or analyzable, right? So in this video, if I was to ask you what's happening in the video, these are automatic algorithms that are processing raw pixels and rendering their representation. On the left are they're called space-time interest points. On the right are key points that are being tracked through optical flow over the video frames. There's motion in the video, but you probably couldn't tell me what's happening here. But if we look at a different video coding or representation over the scene, you can pull out rich content over the video with even much lower dimensional concepts. It's really fantastic how little information you actually need to pull out from the video to get something relevant and interesting. The challenge of video coding is to figure out how to represent the content in a way that I can either easily manually annotate it or easily automatically annotate it, and then in a way that is useful for my downstream processing. Right, so again, my name is Jason Corso, so I'm the organizer for the workshop. I'm a professor in EECS here at Michigan, and I work in computer vision and robotics in kind of all areas of it related to data science, machine learning, and so on, you know, from consumer video to driving video to neuroscience data and so on. Just a side note, as you see on the slide here, I'm actually leaving Michigan at the end of this year. I'm going to Stevens Institute to start a new artificial intelligence institute there at that university. But I'm happy to do this workshop and get the conversation started, continue it with me or hand it off to someone here. With me today, I have three amazing colleagues, Maggie Levenstein, who's the director of ICPSR, Susan Jekielek, who's an associate research scientist at ICPSR. They will be giving the next bit of the talk together. And then also Donnie Likosky, who's a professor in cardiac surgery, who will be talking about the use of video coding in measuring surgical skill and technique. So now I'll hand it over to Maggie and Susan to talk about video coding in education.
Mute. Okay. Hello. So let me, no, not yet. Let's see. I'm not sharing yet. There we go. Share. Okay.
Beautiful.
So is this sharing?
Yes.
Okay. But it's not. Okay. Now let me go. Come on. All right. It's hiding. This is always the challenge when it does this. Okay. It's not, I want it to go, there we go, it's to full screen. Okay, great. So sorry about that. So thank you very much, Jason. We're really excited to be here and to hear about the work that you're doing, because this is something we've been talking about at ICPSR, because the potential value of this kind of coding of video is just enormous. And we can see that from where we sit. I'm going to tell you a little bit about what it is we're looking at that makes us think that this is so valuable. And Susan and I will be switching off, though I'm going to run the slides from here. As we said, I'm the director of ICPSR, which is the Inter-University Consortium for Political and Social Research. And Susan Jekielek runs our education data archives. And we've got actually 5 or 6, I listed 5 of them here that Susan is very involved in. So we're going to talk, I'll tell you a little bit of, for those of you who don't know, I'm going to tell you a little bit more about ICPSR just to give you context. We're based here at the University of Michigan, where we were founded in 1962 by 22 universities. We're actually a consortium. We have almost 800 universities and research institutions around the world, all of whom, and people, those institutions and those researchers give us data, and then we disseminate it to the world. We are the largest social science data archive in the world. And we focus very broadly on social and behavioral science, very broadly defined. We have about 15,000 studies or collections. It's about 250,000 files. About 10% of those are confidential, they're restricted. And that's particularly important when we're talking about video, as we'll talk about in a second. Just so you know, one of the very cool things about the way that ICPSR data is currently annotated is that it includes a bibliography of data-related literature that has about 92,000 citations. So whenever somebody uses the data, part of the metadata, part of the information that you have about those studies are the publications that have come out of it. We also we also provide standard coding for lots of data sets. We provide standard metadata, I should say, for lots of data sets that make the data much more usable for researchers. That the goal of what we do is to create really high quality data that somebody can come and use without having to go back to the original data producer, and that has the kind of search terms that make it easy to find. Because we have so much confidential data at this point, we also have multiple strategies for safe research using that sensitive data. Those include different kinds of computing environments, but those computing environments constrain what we can do, especially when we're talking about video data. And I'm going to turn it over to Susan to talk about the education data that we and the relationship between education and video data.
Thank you, Maggie. So a fundamental research question over the past 2 decades has been in education is, what is the role that teachers play in achievement and social skills of students in their classrooms? And the answer to this question is not so simple. So there are many ways that researchers have tried to address this question. For example, by examining the curriculum that teachers offer, the pedagogy of the teachers, classroom interactions, etc. Those surveys are often used to collect this data. The predominant research method is through classroom observations, through recording classroom behavior and teacher-child interactions. And involved with this coding also is very complex coding schemes where real people are observing the videos and watching the videos and coming up with a coding scheme that correlate to different measures that are related to student achievement, that are known to be related to student achievement. So these might include something like teaching style, multiple changes in teaching or activity switching. I know we're talking about video, but intermixed in here are sometimes audio. So teachers' language and other aspects of the classroom that are seen as indicators for predicting student success. Often the videos are used for this original study purpose and are not often shareable for multiple purposes. And so one real challenge for a variety of reasons is that even though there are often many videos collected for coding, very few end up getting coded, and the data often goes underused, I should say.
Yeah. So, one of the things I mentioned, so ICPSR is a data archive, and people come to us regularly to give us data. And that includes increasingly people are coming, I would say on a regular basis. There's hardly a week that goes by in which someone doesn't come to ICPSR and say that as part of a research project, often a federally funded research project, though some of these are funded by foundations, that they would like to give us data to make those data available to the research community. And in some cases, as in the measures of effective teaching video data that we received from the Gates Foundation, we have taken that data and curated it and make it available in a safe way for researchers who are studying children in the classroom. But there are very significant challenges. The first is that the size complicates the storage, preservation, and access to the data. So it is, we tend to think of size of data as not being a significant barrier, as not a significant cost, because capacity has increased so much. But that is not true for video data, particularly video data that is confidential, so it has to be managed in a careful way. If we don't care about putting our classroom video data up on YouTube, it's much simpler. But in general, the consent forms that we get kids to sign, and we get their parents to sign, and we get their teachers to sign, and their school districts, do not allow us to just put those video up on the web, up on YouTube or something like that. So they have to be stored someplace secure. We also, because we are a preservation archive, we actually, for most of our data, have multiple copies of the data stored in different places. That's also made much more difficult just because of the size of video. Just the challenges of moving video data around. For most of our data resources, researchers just download the data to their local computing environment. In this case, this is the kind of case where really you want to bring the researcher to the data rather than bringing the data to the researcher, that's more efficient way for them to access it. But that means that the video have to be in a secure environment. Again, as we said, it's partly the size, but it interacts with privacy. For a lot of the data that ICPSR and other data archives get that we want to make available that has confidential information, we perform some kind of anonymization. That is to say, we make it harder to tell who the person is who's in the video. But anonymization is often not consistent with maintaining the use value of video. If you want to be able to see whether the teacher is looking at the child, if the child is looking at the teacher, you can't blur out their faces. As in the example you just saw, if you'd like to know how large the group is, you actually need to be able to see the distinct children. And if you blur it too much, you're going to have a hard time doing that. For these data, there are often multiple levels of privacy. So you're not just talking about the privacy of the children or the teachers, but also the communities and the schools that may want to have their privacy protected. Though that information may be very valuable to a researcher. In fact, if there are different kinds of curriculum or different kinds of programming, different kinds of resources available in different schools, but you don't want that information to be out there for the general public. In general, the way that restricted data, sensitive data is made available to the research community is in sort of standalone computers or in safe enclaves. And those are generally not designed to handle video data size. And they often aren't equipped with software that allows a researcher to work with data efficiently. In fact, one of the things, the last is the way that researchers generally work with video data is to run specialized software that allows them to watch the video and annotate it, human annotation, as it goes along. And sometimes you'll want to actually have that done twice for validation of the type of coding that's happening. That's a very, very time-consuming, labor-intensive process. Again, in some cases, Google or YouTube may have that done using, or Amazon, right? Using Amazon Turk. We, again, with confidential data, we do not usually have random individuals look at videos of children or other kinds of sensitive information and code that up. But we have to have a secure environment. We have to engage in that very intensive, labor-intensive process for coding the data to make it useful to the researcher. This creates delays If we're trying to figure out whether an intervention or a program is useful, we won't know if it takes a long time. As Susan mentioned, this really leads to underutilization of enormously costly resources. It's sort of shocking, and I'm not an education researcher, so I guess it's shocking to me, but education researchers and the federal government spend an enormous amount of money creating just amazingly rich videos of lots and lots of different children and lots of different kinds of situations. And most of that is not, is used for one study, right? Is used for for one data collection to answer one question about one very specific population. It would be much more useful if those data were, it would be much more efficient if those videos were made more broadly available. This is particularly the case when you think about how expensive it is to do this. And it's expensive in terms of money, but also in terms of time, in terms of connections to get schools and school districts to agree to this. And that means that junior researchers, junior faculty, less well-resourced researchers are really excluded from much of from access to and from these kinds of research. Given that those data are available, it would be really wonderful to be able to make them more generally available. The last thing I want to say, and this is incredibly important, especially for research like education data, like education research. There's lots of studies that are done on one classroom, one school district. And then we try to make inference about this about policies that are for populations. For surveys, we do nationally representative samples, or we do samples, we take samples of the population that are designed to allow us to make inference about the general population or a broader population than those that are in the study. With video data, because it's expensive to collect, these populations tend to be very small and not representative. But because there's a lot of video data collected, if we had better metadata about it, it would actually allow us to aggregate studies that were collected by lots of different people in different places of different kinds of kids. But you have to have, at a minimum, you'd have to have standardized metadata to say, where are all of the videos of fourth graders studying science, right? Not just did this particular fourth grade, this particularly creative or interesting or, mind-bogglingly boring way of teaching science to fourth graders. How did it work, right? But how did teaching of, what are all of the videos of fourth graders learning science across the country look like? We have absolutely no way of, not of even find that, but even of tagging them, of annotating in them in this most basic way to allow us to leverage these resources more efficiently. And we are really hopeful that some of these strategies can help us address those challenges. Susan, back to you.
So you might imagine that one of the first steps we would recommend is to add standardized metadata to videos of classroom data. It would help improve the discoverability and usability of video data. And Maggie gave a good example of, well, let me just say, without good basic metadata, it would be really difficult and time consuming to make decisions about which videos from a collection of videos to sample for one's own study, let alone combine across studies, which we would be really excited about. Even basic metadata about class size, grade level, topic of lesson being taught. So for example, we have a collection of over 11,000 videos in 1,400 classrooms, and it would be hard for reuse without really even basic metadata. It would be hard for time consuming for somebody to look through and decide how to sample from those videos for the purposes of their own specific research question. And we have found, like some of the even basic characteristics that Maggie mentioned, grade level, topic of lesson being taught, and one thing not mentioned was whether it's the same teacher. Like a teacher ID that's attached to the videos would be really helpful. Some of those characteristics could be assigned, could be manually assigned, but there are those and many others that would be really helpful for automatic extraction of key characteristics that might, for example, help us understand more about class size or the demographics or the setting characteristics of the setting that is being videotaped. It would be very helpful. Again, as Maggie alluded to, it would allow aggregation and reuse. I think that a lot of video studies are of a smaller nature than 11,000 videos. But knowing a few characteristics about the studies might allow researchers to aggregate and increase their power if they can aggregate across a number of videos. And it would leverage existing, though imperfect, use of algorithms that identify people and places. Can you go to the next slide, Maggie? So the second step we would recommend is automating the coding of content of video. This would allow researchers to analyze content without the sensitivity in viewing videos in individuals in specific places. It could also make analyzable video that has not been authorized to be viewed by researchers outside of the research team. And so researchers can analyze the content without viewing the video directly. And there are key measures of interactions of interest to education researchers that are associated with student achievement that also have the potential, we've learned from research outside of education, to be automated or machine read. So these are characteristics such as transitions, disruptions, behavior, disapproving and approving comments from teachers. We say here number of workers, but that's number of words spoken by teachers or students, eye contact of the teacher. So there are and again, I'm mixing some of the audio with the video, but in talking with our colleagues from other domains, that these characteristics are both important to researchers in education, as well as have the potential to be coded. So in summary, we think algorithms to code some of these key measures could transform the use of video data in education research.
You're not mentioning that Data Jeff loves video data, Susan. So so thank you all very much. We want to emphasize that we're really, Data Jeff is our, I don't know, mascot, is that what we call him? But anyway, we just want to emphasize that we're really excited about the opportunities that are created, particularly for education video, but other kinds of video that are created in the research context to improve their usefulness and their value to the research community. So thank you. We're so glad to be here and part of this.
Yes, thank you, Maggie and Susan. That was absolutely fantastic to hear about video coding, the intense need from the educational side, and to touch on things like privacy and cost, right? And the need for standardization. All of that it resonates intensely well with someone from my background, which is much more at the sort of technical, foundational level, to unlock what may be possible in improving standardized automated video coding. So let's see where I think we need to go. In some sense, there's a lot of words in these slides, but if we start at the top, right? So let's just get a definition here, right? So like concretely, in my view, video coding is the translation of video, which, Susan, may include audio. So there is some work in automation or computer vision, machine learning that does make audio video synonymous with video, if you will. But video coding is the translation of video into human or machine readable annotations to facilitate downstream study, downstream inquiry. And as we've all identified, or as you both mentioned, right, at the core of this is the extraction of information from video, which is challenging on many fronts, right? So it's challenging because, as you said, Maggie, the data may be secure, private, We need to worry about the, those concerns. I'm not going to talk too much about that, or really any more about that, because you did it great justice. And there are not great answers to that right now, really, except for there may be some researchers looking at how to better anonymize video so that it can be coded by humans, if you will. But that's a big challenge here, and it's even more like, and then you mentioned Mechanical Turk, right? It's like the like crowd-based annotation of video. So although it's used somewhat widely in video or image and video coding of non-sensitive data, it is not trusted so well, right? So, and that's because of your step one, right? The notion of a standardized metadata schema, right? So that there's like, without a standardized metadata schema, which I'm here calling an ontology, right? So, and that really works at two levels, right? So I think to some degree, you were talking kind of at a low level, like what are the fields we need in our schema? How do we think about them? How do we represent them? And then how does that allow for sharing and cross-site annotation, cross-site utilization of data? But I also mean an ontology at a higher level. And to give you a good example that has come up, time and time again, is the notion of grouping, right? Like, if I'm just doing something very simple in computer vision, like detecting vehicles that we think of as sort of automatable, offhand, pretty straightforward now. We have to decide what to do when there's one vehicle in view, when there are 3 vehicles in view, when there are 10 vehicles in view, and when there's 100, like when it's a traffic jam in downtown Manhattan, right? Like, and that's hard to do, to specify at an ontological level in a way that is translatable to the annotators themselves, who might be humans or might be algorithms, right? It's very difficult. It's kind of an open-ended problem right now, how to translate the need to make a concrete representational definition or ontological definition specified in such a way that we can reduce that to an algorithm of activity, either by humans or by machines. And I use ontology lightly here. I have worked with some philosophers in the past who would probably be balking at my use of the word here, but I think it's a good holistic word to use for the notion of writing down a representation, a taxonomy at both a high level and a low level in terms of what we want to represent. But I think that's a core component of video coding. I think the second core component of video coding is the specification of a protocol of annotation. How when you're teaching a human to do it, or what you're expecting a computer to annotate, right? Like how to go about it, what's important to look at first, what does this type of event mean, what does that type of event mean, and so on. That also includes how much we want to automate the annotation or the video coding, right? So I think, and most of the next bit of this workshop will be my view of why it's hard to automate, because that's really the key here, right? If we could automate it better, then we could have reproducible annotations that are trustable, that remain private, and they're shareable, right? We could unlock, huge amount of downstream inquiry. And so I think of this as a spectrum, really. So on one end of the spectrum, we have strictly human-based annotation, but even by experts in some sense, right? Highly trained annotators who know exactly what to do, fully understand the protocol, no risk of them competing for the right answer. This is in some sense a holy grail, not an inachievable holy grail, right? Like even in the case of like reading radiographs, I've worked on some medical problems in the past. You have a situation where 2 radiologists will disagree on the same radiograph, and it's natural. It's a complicated signal. So, but anyway, human reading is at one end of the spectrum. At the other end of the spectrum would be automated computer algorithms. These are things in the fields that common words like artificial intelligence, computer vision, machine learning, data science, they all kind of mean the same thing in the context of video coding. Basically, video comes in, runs through a computer program, some other format comes out at the other end, usually in a machine readable format that might then be visualizable by humans. In the middle, along these 2 ends of the spectrum, are where we are today, really, right? So very rarely, at least in lower level computer vision type research, are we doing strictly manual annotation. Oftentimes it's interactive, like seeded by some computer vision algorithm and then refined by humans, such as like, you want to do counting in a classroom, fine. the computer vision algorithm will propose a count and render to a human the number of faces that it sees, and then a human observer, even an untrained human observer, then can go and look at and click on or off certain boxes. Then we have a closer to automatic is a little bit more online learning oriented or semi-supervised, where there is a human available, but it's, you know, the burden is really on learning from the human's answers. This is sometimes called active learning or active clustering, but the notion that we have a method that will listen to what the humans are, or observe what the humans are annotating or coding, and then be able to get up to speed to reproduce that work more efficiently, more effectively. Third is the specification of the nuts and bolts, really, the data format, where the data lives. Maggie could not have been more correct when saying with video, it is not just a problem of specifying what file format you want and putting the data in the cloud. You really need to bring the person or the code to the data for video. It's a big problem, even for big companies. You know, I was talking with an investor a few weeks ago who told me, if you guys have invested or created a technology for interactive streaming of video with the annotations on it, that would be a game changer. And we totally agree, right? It's very difficult even just to visualize data that's in a cloud bucket, for example. And then finally, we want to execute the work, right? So for the next 15 or so minutes, I'm going to give you more of an intro to computer vision in some sense to help you understand why it's hard to get automatic, right? We really want to get to the space of automatic video coding, but it's a challenge and it's fun. I personally invested my career in this, but it's hard, right? So let's start to understand what information is in video. Like what could we actually extract from images, from video, and even from audio in some sense, right? We think of this in the space of computer vision as really stratified into 5 different layers, right? So at the top, I should have these flipped actually because they go from sort of early low-level processes to later high-level processes. But anyway, first you have early processes, things like features, edges, contours, segmentations, points of interest. You can map these to things you've probably heard of in social science work, like facial action units. I think is a big deal here. Like what points on the face are responding to when certain emotions or expressions are being conveyed, and so on. Next up, if you will, is motion tracking. I take basic features and then track them through time, filter them to make sure that the ones that are being represented are the appropriate ones that we want. Then we have things that are kind of like in the mid-level, right? Like shape type features, 2D structure or 3D structure. Like if we're doing some type of analysis, maybe Donnie might pick up on this with pose, or we saw in the hockey example, right? Like you have the shape of the hockey player taking a slap shot, you know, the angle between their upper arm and their lower arm, it's critical to do that type of analysis. And then after that, you have objects, and then finally actions. And these really are the core of the different classes of information that we may want to extract when doing video coding. How we do that is a challenge, right? And so how do we think about, okay, we have those classes of information. Now, how do we map that to problem definitions for computer vision or video coding, right? So take this image. Maybe you may know where this is, I'm not sure. So let's problem name 1, right? Classification. Asks a question like, does this image contain a building? It's a yes or no answer, binary answer. One could imagine a video coding for this, right? Is there a teacher present in this classroom? Is there a surgeon's tool present in this video? That kind of thing. Other classification questions may be about the whole scene rather than things in the scene, right? Like, is this a beach? Is this a city? Is this urban? Is this nighttime? Is this daytime? These are all very relevant, pretty early processes or simple questions that we could ask about it. Next type of question we could ask is a detection question, which asks not only like, is this thing present in the image, but where is the thing present, right? So where is the car in this image is really a detection problem. Usually with detection, when we start to think about metadata, we have an identity or a class type, a car or teddy bear or clock, and then also a bounding box in the scene, in the frame of the video that we're tracking. if you think about then how you would actually write some code or represent this detection in a video, it becomes much more involved, right? For one image, it's just a bounding box, upper left, lower right, ID, 5 parameters, we're done. When you have a video, you have 30 frames per second, maybe 60 frames per second. That car can be moving, the camera can be jittering. You may get spurious detections if you're doing it automatically. That's where the real expense in doing it automatically or doing it manually comes in, right? I have to check every single frame of the video to find where this may be, right? Really complicated to do manually. Detections may ask more complicated questions even too, like, where is the building in this image, right? Does this contain a building? Yes, but the building is layered, right? There's a clock on the building, there are windows on the building, right? So you might be looking for more structured information like that as well. Here's a good example as well at the bottom of this notion of grouping, right? This is a person, yes. This is a person, yes. This is also a person, yes. But this is a crowd of people crossing a street, also yes. So when I'm thinking about how to evaluate automated video coding methods, do I evaluate the group extraction or the individual extraction? And if I'm going to do it for both, I have to annotate that in a bifurcated sense. But if I'm doing it for individual, then I have to annotate and know how and sort of track the provenance of my annotation or my ontology there. It gets really complicated. Another problem definition that we think of is called semantic segmentation. So for every pixel in the video or in the image frame, video frame, tell me if that pixel is part of an object of interest, like a clock in this particular case. So it's kind of like classification and localization jointly at a pixel level. And then you also may want to ask about what the semantic and geometric attributes of things you're finding in the scene are, right? Like there is a building, it is a 45-degree pose, 8 to 10 meters away, it's made of bricks and so on. Or here's a car, it's a police car, it's a side view, 4 or 5 meters away, it's a person, and so on, right? So you can imagine the rich set of questions you want to ask. So you're sort of layering these questions on top of each other as you're executing your video coding, right? Another notion is the difference between categorization versus single instance classification, right? This is a building, yes, but if I ask you what building it is, some of you could probably tell me that it is the Marshall Field building in Chicago, right? So that's the difference. Single instance, Marshall Field, categorization, a building, right? Same thing when you're shopping in the grocery store here for different cereals and so on. I never take my kids to the grocery store because we always leave with Cinnamon Toast Crunch, and we meant to leave with something more healthy than that. One thinks of video as like the temporal activity in the video, fine. That's also where activity or event recognition comes in. We could have spent all 90 minutes just on how to stratify the difference between action, activity, interaction, events. For the sake of video coding, let's just say one can ask many questions about the video, and we can stratify those according to a increasingly complex amount of information, right? So that's like what we can extract, what we call the problems in computer vision for how to actually extract that information. But now the actual extraction of the information, well, that's really hard. So this is an image that's rendered for you in a different way than you normally look at images. So what you see here is a horizontal, this is a 2D image, the vertical axis, I think you can see my mouse, and the horizontal axis. Instead of the grayscale at every pixel, the brighter the pixel it is, the higher off of the ground plane is rendered in this 3D surface map. So I'm wondering, this is a real image, a photograph. I'm wondering if you could tell me what this is an image of. Normally I would wait, you're thinking what it might be, and then I'm going to show you the answer because I can't actually query you in this webinar. That was the image. Now, if I go back, you can look at features, look for the mirror and look for the brim of the hat and the feathers. You can see them in the heat map. Here's the mirror. Here's the brim of the hat and the feathers and the shoulder, right? This is really hard to do automatically because the computer system doesn't see what we see. We're not, we've been seeing more data since we've been a baby than most computer vision systems see to train in modern deep learning, right? So the challenge is that, like, when we're presenting this information to a machine learning system to actually learn, it has no prior, it has no context, nothing to map its own experience on, to map the impact of moving this way. What does that get me? Does that get me a snack, or does that get me to my bed, or get me to my mom, things like that. Right? There's no context, no prior. All it sees are a grid of numbers which map to photometric intensities of the scene content mapping to the actual data. So the challenge of a machine learning system for automated video coding is to map these numbers to hat, brim, eyelash, slapshot, beach, things like that. It's really challenging, right? So if I give you images that try to tease out and test against your prior, you might be convinced maybe a little more that it's hard, right? So can you see what object is in this image? This is a hard image for a human to see normally. Until I tell you it is an image of a dog. And then you can see the hind leg of the dog, and the head of the dog, and the front leg of the dog, and the other front leg of the dog, and the whole back of the dog. Amazing. I just told you one word and you can now interpret the scene. All right, that's because you're expert seers. Are these straight lines, or are these lines at an angle? You know who these people are, I think, right? Are these, it's interesting to give this in an election week or post-election week. This is Bill Clinton and Al Gore, right? No, that's the same snapshot of the same face. That was Bill Clinton and Bill Clinton, but context gave it away in that case, right? It's really amazing what you can do with computer vision, or why computer vision is hard, right? So again, context counts as much for appearance. It's really a hard AI complete problem. There's really a lack of a clear metric or loss function. Like, when do we know video coding is working, right? Just like back to the first video, that's why I asked it, what, about how old the girl was in the birthday party. When you're doing the video coding, even automatically, you may not know what question the scientist really wants to ask. So you do the video coding, you train a whole algorithm, you spend 6 months on it, you get what they asked for, and then they come back and say, yeah, but I really wanted to know how old she was. You're right. So getting to that full-scale generalized understanding is a really hard problem. And it's hard because of a lot of different reasons, right? There's viewpoint variation in real images. There's illumination variation. There's scale variation. There's deformation, articulated objects. There's occlusion that make it really difficult to understand in natural scenes what different phenomena look like. There's background clutter that is oftentimes confusing and unclear. There's a lot of variation in terms of what things look like and then what things can do, right? Like, the chair is a great example that a lot of AI and computer vision people like to talk about as being a real hard example, because really anything can be a chair. Anything that can support some weight is a chair. But we don't always think of all things like that as chairs, right? Like, here are lots of examples of actual chairs, and they all look very different. It's interesting that yet my 3-year-old, I can tell her a definition of something she's never seen, like a snurble, is a big puffy round pink thing, and then she can go and find it in her shows, and she's great with doing that, right? Like, that's the big challenge here. And there's also many different classes of objects in the world. The number 10,000 to 30,000 here comes from some literature in psychology about the number of sort of nouns that humans can are sort of aware of or attend to. There may be more different variations in classes just because of the different scale or resolution at which we're looking at different phenomena. Also, ambiguity is a problem, right? So here, this is something Maggie mentioned a little bit earlier, right? So privacy, let's map this case to privacy, right? Like, here's a scene of here's a blurred image of a scene. You already know what's happening here, right? I'm gonna tell you what you're thinking. There's a guy, looks like a guy, at a computer who's talking on the phone. That's what most of us are thinking right now. But it's actually a guy holding a shoe up to his ear, and he's looking at an upside down garbage can, right? Like, when you don't have enough pixels or enough information about it, the actual data may vary. right? So take a look at this as well. Here's just a blurred snapshot or a blurred patch or small region of an image. Where is that patch in this scene? Is it that one or is it rotated, right? Is it that phone? Is it one of these three? One of those two, right? So these are sort of fictitious examples or contrived examples, but it gives you a good sense for sometimes I need more data, sometimes I need less data. Understanding how to train a model for this is a big challenge, right? So this other notion of ambiguity comes from the fact that we are living in a 3D world. In video, we think of it as a 3D world plus time, right? But what we actually see is a projection of that 3D world down onto our image plane. We can be very tricky as we do that, right? So you see the fancy photographs here, beautiful chalk artwork on the ground. I think there's actually my family has a sketchbook or a picture book of a famous artist in Ann Arbor who does these types of chalk drawings on different ground on sidewalk. Really, really fantastic. Similarly, like some scenes are unique, right? You probably are not going to see them often, right? But not all scenes are that original, right? Like I can have, this is a city street, right? But there may be some nuances about the scene depending on what you're coding that make it interesting, right? This is a scene of a pharmacy. No pharmacy in any of other scenes here, right? You can probably tell even where these, what region in the world these may have come from. So it really depends on what question you're asking. Right? But, I'm giving you all the bad things so far, the hard things, which are fun for scientists, I guess. It's good that it's hard. But it's not all wasted time or lost effort, right? So we have made a good amount of progress over the last 20, 30 years in computer vision, especially at these high level problems where we look to, like the ontology involves things that involve like language type descriptions, right? So this is really talking to the advances we see in deep learning. While some of my colleagues across the world may think that deep learning will give us all of the answers, I don't share that confidence or that truth, but I do still see a huge amount of good progress in the promise of being able to take large amounts of labeled data, probably too much labeled data than we should need, and then map that to the ability to recognize digits in arbitrary photographs or very, distributions over possible objects across many hundreds or thousands of objects, or the ability to retrieve, given an image query, to retrieve like images from a very large database. This is done through a sequence of composed functions, oftentimes through convolutional layers and linear layers or different types of pooling layers and so on. I won't go into the details here, but they have millions of parameters that are tuned or mapped based on these labeled training data to give you these automatic codings. As long as your training data somewhat matches your application data or your test data, you'll tend to get decent enough video coding, at least enough for the interaction type of real video coding where you can prime the human with possible answers and then they'll go through and check them. You can map these layers to the earlier low, mid, and high level layers that we talked about earlier, right? Like sort of start with the image, map those to things like edges and points and so on. And then you start to get mid-level things like shapes and connected lines and contours coming out, and ultimately high-level things that we can describe or attribute words to. And then finally you have the output video coding. Right, so we see this in faces, we see this in cell biology, we see this in video classification directly. So this is an example of a network that separates, just like in the mammalian vision system, separates the spatial information stream from a different temporal information stream and then fuses them together, much like is believed to happen in human vision. And this is just a comment that there are many different ways of solving these things, and these are called models. Each computer program that translates video or images into some automatic output as a model. It's not as easy as just going to like download the model and run it like you can some arbitrary program, because you really have to think about the representation that you want to seek. But it's at least confident that you can work with a technological person, a technically capable person, and sort of get toward a system that might improve or speed up your automated video coding or semi-automated video coding. All right, great. So now is Donnie's turn, but I don't see Donnie's picture in the set anymore. Did we lose Donnie?
So he is not here. He's not logged on. I did see someone posting something that's saying that lights were flickering on and off. So he may have lost power. Do you want to just continue, Jason, and we'll come back to Donnie if he gets back on?
Yeah, I can do that. Let me just send him a text since I have his cell number quickly.
Yeah, someone just said there was a power outage on North Campus, apparently. So that would be my bet.
I think I have a copy of Donnie's slides at some point. I could probably give him, since it's a joint project, but he talks about surgery so much better than I do that I don't think I should give it. I'll butcher maybe that verb. I'll not do it justice. So we can come back to Donnie indeed. So the next bit I wanted to talk about is, Donnie was going to talk about surgery. To give you another example of how video coding can drive various scientific inquiry. The next tool, though, I wanted to talk about, the next bit after that was going to be just an overview of open source tools for video coding, right? Like when Maggie was talking about it earlier, she mentioned like usually you have the video uploaded somewhere in some database or some cloud storage somewhere, or even local data system. But then in order to access those videos, you need the right tools. Those are non-trivial for video. Even just like, preview, if you have an Apple or a MacBook, there's QuickTime Player that will play some videos out of the box, but not all codecs, right? So you need to get a different software called VLC, right? That can play many different codecs. So having the right tools to work with your video data is critical. So let's think, and this is all again in the context of automating video coding for more rapidity, more sharing, and so on. So I kind of think of the problem space as having three components, right? So there's the data part of it, which is the actual video data. Okay, Donnie's trying. We'll see if he can get back on. Just a side comment, Maggie, if he's like joining but not a panelist, maybe you can click him as a panelist. But okay, so the data side is where your data lives, how you represent it. File formats like VLC, for example, is a good example of a player for videos, and those components of it. And then after that are the model part of it, which is the computer system, the training, the data science that will go and take that data and produce a program that can output automatically these annotations, right? The video coding really. And then after that is the analysis. And this is a loop, right? It goes hand in hand. Usually when you're training an automatic or semi-automatic method, it's not going to be a fixed one-time thing. You're going to go and get some data, annotate it with some humans, go train your model, go back until it reaches a performance level, or your scientist that you're working with agrees that it's good enough in some sense, meets the right metrics, and so on. So this is kind of a loop. So where are the open source pieces along this cycle here? So Intel produces something called CVAT, which I'll talk a little bit more about next. That's for annotation. It is a world-class annotation tool that will render images and video on your computer or on a remote cloud-based storage, and let you or your team members go and watch the videos and draw the annotations on it. Very easy to use for novice and experts. And then there's another tool called Pachyderm, which is for versioning of your data. One thing we didn't really talk about so far is we talked a little bit about provenance and privacy, but versioning of data and data sets is really critical as you do your analysis. So Pachyderm is an open source solution for that. And then on the model side, there are tons and tons of open source frameworks for actually doing the automated analysis. Things like PyTorch, NLTK for natural language, Keras, TensorFlow, you name it. There's like a language, and most of these are supported by companies now, surprisingly too. So it's fantastic how much open source there is there. But then as you're doing your analysis work or your model training work for your automated video coder, there's an open source tool by a company called Databricks that's called MLflow, which is fantastic. I've used it in my lab for maybe 3-4 years now. It lets you track in a cloud-based or local distributed cluster type system, your experiments, all the different parameters that are being taken there. And then down on the analysis side, there are 2 tools, one for visualization of models and aggregate performance. This is called TensorBoard. It's like a web-based interface released by Google for TensorFlow, but web-based interface to track how your different experiments are performing in aggregate over data sets. And then more of a visualization / analysis tool by a local Ann Arbor startup, my startup actually, called Voxel 51, open source called 51, which really lets you do the type of data subset analysis that you're looking to do. So why don't I go just through a few more slides, Donnie, and then we'll come back to you for your bit there, just since I'm in the middle of this here. So just a couple more slides about CVAT, since I just think if you don't know about it, those of you who are attending, this will be worth your while to check it out. It is an excellent tool for human annotation with some automation of video and images. It's for organization of data, annotates, it handles all different problems like semantic segmentation, classification. It's suitable for direct video coding, as well as building training data sets for then later downstream AI video coding. And it has the MIT license, which basically means it's free for however you want to use it, and they have no liability for it. It supports many different formats, like Pascal VOC, YOLO, TF Records, Label Me, CVAT. If you don't know what that means, don't worry, these are just common formats, both for input, import, and export. And it also has existing models, like I was just talking about earlier, that are available in its framework to automate, or again, semi-automate the annotation process. It's easily deployable locally, or they have an open web-based tool that's demoable, as well as a command line interface. And it's also deployable in Amazon Web Services, which is fantastic since the vast majority of the world's data lives in AWS these days. And then a couple slides about 51. This tool lets you really rapidly experiment with your data sets, analyze them in aggregate, performance measure like precision recall, semi-aggregate, like lots of images at once or videos at once, and then in detail, as you saw in that slide there. It lets you do things like choose optimal samples, remove redundant images or videos, find mistakes in your annotations, which are critical. Like Maggie mentioned, this notion of having more than one person do annotation on one video. This is a tool that really lets you help find those types of mistakes. It doesn't use the Apache license. It doesn't use the MIT license. It uses the Apache license, which is essentially as free as the Apache license. So free open source on GitHub. It lets you do things. Other aspects are finding near duplicate samples in your data by ranking them according to some state-of-the-art machine learning algorithms. You have an interactive capability to manipulate thresholds. Another way of thinking about this type of tool is that it creates like an innovative query language that lets you very quickly ask questions about your data set in aggregate, and then look at the subsamples in which those things are true. And this is just more example. It also supports all common visualizations for common vision tasks like classification, segmentation, over image and video data. And one innovation for the coders that are attending is that it has a really, really clean handoff between the code and the GUI. So basically anything you do in the GUI is available in your IPython shell. Anything you do in the IPython shell will be represented directly in the GUI. So it's a pretty cool handoff there. So at this point, why don't we have Donnie take over and go through your bit, and then we can take questions after that. I think we'll be right on time.
Thank you. I'm sorry that I got kicked off my Wi-Fi earlier. Hopefully, can everyone see my screen? Okay, fantastic. My name is Donnie Likosky. I'm a cardiovascular epidemiologist and am working within the space of computer vision, although it makes me quite nervous. And so as I was thinking about this and how to set rapport, given that I haven't spoken this forum before, I tried to figure out whether or not the RSVP should have said yes and whether or not the invitation went to the right person. What I want to say is basically I'm an end user. So I work in a space, I to navigate the space with my friend Jason and others. But what I am is excited to share with you how our team involving Jason and others is advancing real world outcomes for the patients whom we serve, which are cardiac surgical patients, using computer vision solutions. So here's an example. So let's say that you're interested in understanding how to manage your obesity and you're looking for a bariatric surgeon. So if you go up to Google, you put some information in related to bariatric surgery and how to choose a surgeon, and you might see this, here's some hints. You ought to get a referral. You ought to research the surgeon's credentials, their experience, consider gender, so on and so forth. Well, what's missing? What about the surgeon's skill? Because at the end of the day, you want to make sure that the surgeon actually is gifted. Well, how do they do this? How do they do this operation? This may be more information that you want to know, but just give me a little bit of time. So they basically often will put little holes in your belly, and then they look at the inside of your belly to try to figure out how they're going to do the operation. And this is what they see. They see these tools and they make their basically sewing of different parts of your belly. And some of my colleagues actually have studied to what extent an assessment of a surgeon's technical skill actually is associated with outcomes. What they did was they asked surgeons to submit videos. If I were a surgeon, you know what, I would do my due diligence and make sure that I pick the right video to send for peer assessment. So basically I'm asking my peers to rate my skills. And then they ultimately linked the assessments of their peers of that surgeon's video to the last 2 years of the surgeon's complication rates. So on the x-axis here, they have the assessment of the surgeon's skills. And the y-axis, they had the assessment of the complications from that surgeon. And so surgeons in this area, they were rated high in terms of their skill, and they had super low complication rates. And surgeons in each one of these dots is a surgeon. Surgeons up here, they had lower ratings of their surgical skill, and they had higher complication rates. So basically, impressively, if you will, they found that peer ratings varied by surgeon, and that lower ratings of your skill were associated with having higher complication rates. Well, I'm not in the bariatric surgery space. I'm in the cardiac surgery space. And you know what? Everyone wants to be different, but I'm going to tell you that cardiac surgery is different than bariatric surgery. Why? Well, you see these things? These are funny looking glasses. These are called high magnification of your view. So we're looking at super, super small little vessels in your heart. And you know what? In cardiac surgery, we often take the blood out of your heart and put it through a machine, and we arrest your heart with some chemicals. So it's super technical, not to say that bariatric surgeons are technically gifted or work on technically challenging areas of the operation, but you know what? This is super technically challenging. You know what we do? And I'm not a surgeon. We globally, in my space, what we do is we reconstruct the anatomy of your heart. So what? Cardiac surgery is different than bariatric surgery. What we have often done in this space is actually simulated the assessment of a surgeon's skill. So not taking it in vivo, not in real life, but in a simulated environment. And we put these little probes on a surgeon's hand and we assess the way the surgeon actually conducts the operation in these simulated scenarios. Well, you know, cardiac surgery is also different. It's not a solo sport. As Bo said, no man is more important than the team. No coach is more important than the team. The team, the team, the team. And if we think that way, all of us, everything you do, you take into consideration what effect does it have on my team. And so again, different than bariatric surgery, this is the space that my colleagues work in. This is the operating room. And it is an orchestration of all these individual team members who have different tasks, but those tasks are codependent upon one another. It involves the cardiac surgeon located here, a scrub nurse, assistants, this may be a physician assistant and a resident, and then the anesthesiologist, and what you don't see here is a cardiovascular perfusionist. They actually manage the patient's physiologic needs while the heart is arrested and blood flow is not going through the heart. So these are called technical skills. This is the communication, situation awareness, decision-making, leadership, all the things that are also important within cardiac surgery, and then have also been associated with patients doing better, above and beyond how gifted your surgeon is. So in summary, what we often see in the cardiac surgery space is that the complication rates are not just dependent upon the surgeon, they also vary across hospitals. In some instances, 1 out of 10 patients may develop a complication. In another hospital, 3 out of 10 patients develop a complication. And when you collect thousands of variables, which our team does around every single patient, it still holds that only about 2% of that variation in some outcomes are explained by the things that we typically collect. How old is the patient? Are they male or female? Do they have diabetes? So on and so forth. And in some respects, peer-based assessments, as I showed you in bariatric surgery, vary, and they are associated with complications. And also, what's important is if we try to do this across the 300,000 operations that are done every year for cardiac surgery in the United States, we think, based upon Jason's expertise and others, that we can leverage technology to actually automate the things that we aren't currently collecting to help try to identify ways of reducing the variation and complications and making cardiac surgery safer and more reliable. So we have a grant from your tax dollars and others' tax dollars to identify and promote wide-scale adoption of evidence-based surgical practices in 3 unique ways. One is to assess in vivo, in the real world, a surgeon's technical skills and whether or not they actually are associated with complications. Because we know it in bariatric surgery, we don't know it in cardiac surgery that I've already tried to argue is different than bariatric surgery. We also want to know about peer-based assessments of these non-technical skills, the team, and whether or not these non-technical skills are also associated with complications. And then we want to assess the feasibility of using computer vision to automate the assessment of important technical skills and non-technical skills. And this is our setup. This is a patient sits. This is his or her heart. The surgical team is associated, works here. And then we have a camera here. We have a camera here, and we have a camera here. And we digitally record the operation, including audio and video. And then Jason's student, Nathan Lewis, who's getting his PhD, is working with us. And what he's been doing is taking readily available video available through the internet and actually annotating the data and articulating the hand pose of that data. And you see here the good work that Nathan's been doing with our team to automate the assessment of technical practices or technical skills that would otherwise not be collected through readily available data. And the benefit of this is it's not really looking at specific instrument or tool used by the surgeon or the surgical team. And thus it's also transferable to other procedures, not just cardiac surgery, but other widely used surgical procedures. And what we found is interesting that there's some things that we theoretically suggest from expert surgeons are important, we can actually track. So for instance, it's important from a surgeon's perspective to not actually use the hand that actually doesn't have the instrument. And so we would imagine that there'd be less distance traveled for a surgeon's non-suturing hand relative to his or her suturing hand. And in our preliminary data, we suggested that actually is the case. Well, we also think that computer vision has a role in identifying features associated with these non-technical skills. And we think, for instance, that potentially important areas that we should be tracking include whether or not people are looking at the monitors. Here's a monitor. Whether or not team members are closely associated with one another in proximity, and where their faces and hands are actually pointing. And so you see here some preliminary data where Nathan was actually able to identify unique individuals who are part of the operating room team. Well, that's all well and good. Our preliminary data suggests we can actually do this, but what are some operational challenges that we need to consider? Well, you can imagine that this is really a sacred space, and it may not be very accepting of all team members or institutions to actually record in the operating room. It's important that to know that not all operating rooms are equipped with the ability to digitally record in that space. It's a very high-risk environment with medical legal issues that we need to be mindful of, and we design a regulatory pathway to ensure that these data are protected from discovery. We need to have some degree of standardization of what the output and where these recording devices are located. And we need to have a solution that is available to get to scale. And the fact that within the cardiac surgery space, there's 300,000 of these done every year in the United States. There are also some important computer vision challenges that we perhaps need to consider. One is, are we speaking the same language? Jason and I both speak English, but we're from different disciplines. How does my team from the cardiac surgery space communicate with Jason's team so that we're on the same page about what our needs are and what his needs are so that we can advance together? In cardiac surgery, there's a lot of phases of the operation, just like a novel. And we would benefit from having some type of automated or semi-automated way of segmenting videos for analysis by Jason's team and our team. It's important to figure out a way to address privacy and whether or not we can anonymize video and anonymize the audio of these recording devices to protect from discovery. We need to have a way to automate or semi-automate the hand tracking tools to reduce the human input needed to do this at scale. It's also important for us to consider the context. These hands in this movement may be considered to be good from a technical standpoint or not good from a technical standpoint, depending upon the context of the operation. Measurement's important. Some of the things that Jason's team and our team have been focusing on is the ability to assess teamwork by the transfer of instruments from one individual to another, to be able to look at not just the lateral movement, but the vertical movement of hands. And we can only analyze the things that we can actually see. So we need to be able to figure out a way to perhaps infer where the human digits are, because we may not be able to actually see them. And it's probably also important for us to consider the audio. Most of our work thus far has been focusing on video, but you can say the same thing, but say it with a different amount of inflection and have different inherent meaning in that audio. And teamwork is so important in cardiac surgery, and having a sense of how we can analyze the audio is really a necessary component to advance quality. And also we can measure, but does it matter? So we've been talking about the ability to measure the hand movement or the instrument tracking, but does actually correlate with gold standard sources for assessing complication rates. So in conclusion, I think computer vision is used to advance the way we assess quality for cardiac surgery, and if we can do it right, at scale. But there are additional challenges that we need to really figure out together. One is the acceptability of this approach within the surgical space. We need to advance methods to meet the needs and to meet the way that cardiac surgeons and cardiac surgical teams think about quality. That gets to the point of identifying what matters. and ultimately to produce solutions that don't meet the needs of 5 centers or 6 centers the way we're doing in our current grant, but really to potentially meet the solutions at scale across the 1,100 open heart surgery programs in the United States and the 300,000 of these that are done every year. So thank you so much for the opportunity to share my perspective.
Great, thanks, Tony. And I just have one thank you slide. I think. Yep. Right. So, we've heard a lot about video coding today, different consumers of video coding. I tried to give a sense of what the main challenges are, getting toward the automated reality of video coding. But now, I'd like to, certainly take your questions. Just note that if things come up afterwards, I'm happy to take email questions, as I'm sure my other panelists are as well. And just to provide you links to the 2 open source tools that I went to some depth on just before Donnie talked. But just before that, thank you for your interest. I'll stop sharing the screen now, and we're happy to take your questions. I guess the best way to do is probably raise your hand in the Q&A, then we'll let you talk. It's probably the right way to do it. Any questions?
So, Susan, go ahead.
I have a question about, as a researcher, how do you know if your video is of a level of quality that it could be machine read? I mean, there are probably 2 questions, some for later on, like knowing even from the beginning how to start your project so that you are recording in a way, but since there's a lot of video already out there, I guess that's one of my questions. Is there a minimum level of quality needed?
Yeah, actually, Donnie can probably answer that, because we've had so many calls about that in respect to the surgery problem. I guess, Susan, there's no clean answer to that question, because it does depend not only on readability of the video, but on what you want to read. Like if you're just like daytime versus nighttime, you can probably have a pretty grainy, low resolution image or video, or low frame rate video. So it's not going to matter. But if you're talking about an analysis of someone's golf swing, for example, you want highly resolved, really finely detailed video. From a computer vision or machine learning point of view, it is an open problem to quantify how hard a given sample is. If that would be a Turing Award, I think, or whatever, that would basically be like a highest prize in AI, in my view. If one could come up with the right theoretical basis for and practical exposition of or demonstration of quantifying how hard a certain problem or a certain task or a certain sample is, that would be fantastic. We don't have answers there. So you generally are stuck with people like me who have a sense for what's going to happen, and then we'll demonstrate it empirically and then measure statistical significance of our outputs on whatever samples you provide, that kind of thing.
Yeah, the only other thing I would add, because we're trying to get through this with with our team, is also what's practical. So you can have an idealized solution set, but it actually doesn't meet the practicality mandate to actually get it done. And that also includes, do you also have the right context for that video? So maybe it has the right pixels, but you actually don't have the right angle. So I think it becomes a very difficult problem that probably is iterative, and potentially it's also project specific. I'm not sure if that's fair to say as well, Jason.
Yep, absolutely. Yep. And I noticed that Carol has I've given Carol speaking ability, and there's also a question in the Q&A that I'll answer after Carol.
Yeah, hey, this is Carol Flanagan, and wow, that's a lot of power, speaking ability, granted. Anyway, sorry. Hey, I really enjoyed this. This was great. And I love that you guys are talking about it. So here's the thing that I think about a lot has to do with, so for me, the holy grail is to have the computer vision algorithms run across these videos and bring us annotated data. Because frankly, I don't really want to mess with the videos any more than other people want to. I want to just be able to analyze. But the algorithms, of course, are going to impose their own confusion matrix, say, on the data if they're less than perfect. So what do you see as sort of especially let's say in education, which seems like a particularly hard, challenging and interesting problem, what do you see as sort of the low-hanging fruit for demonstrating a truly a true reduction in resource use, right, to do the analysis? So you run the algorithm, you get a bigger sample, maybe you have to check everything, but you genuinely get new results. I don't know, that's kind of what I'm getting at, but did that make sense?
Yeah, I think it makes sense. I think the real base of the question is, how do you know where to start when you're trying to automate video coding in some sense, right? Like, if that's not really like the base of your question, then let me know. But I guess my view about that would be, right, like we are, for decent quality video, we've made, as a field, made good advances on two problems really. Like one is on detection of common phenomena at a resolution, granularity that is straightforward, like person or desk or car, right? We're pretty good at that as a field. Not perfect. I think we have challenges for things that are like far off in the distance, for example. I think we're pretty good at that. And I would always want to start with something like that first. Attributes, for example, like to take the car example, like the make of a vehicle is much harder to do inference on, even though it's just a classification problem. But that's that. And I think another aspect where we've made a lot of progress on, which may be a surprise to me, to you, I don't know, but is pose estimation. And I think that's really relevant for education too. For example, like the ability to understand where the shoulders are, where the head is looking, where the torso is facing. That, especially for education, that seems to have a strong amount of impact toward understanding engagement and other things. And we're pretty good at pose estimation without that much occlusion. When there's occlusion, it's much harder. But it would also be harder for humans to rate those videos, which would lead to more costly and time-consuming engagement, though, too. Yeah.
Jason, can I ask one question about that? So I presume it's also our interpretation of pose and its inference may depend upon people's and their perspective. And so I guess the question is, how do you incorporate, culturally, an individual's own culture in interpreting what you see? And how does that impact the annotation?
I want to lump that type of a challenge into the ontology bin, right? Like it's part of specifying the protocol for what you're looking for when you're doing certain annotations, I think. Yes, there will definitely be cultural differences for things like pose. But that it might almost be in the interpretation of the raw pose, right? There's always like okay, where's the shoulder? It's a fact in some sense in the frame. Then you can try to normalize it to like a body-centric pose, right? Like instead of independent of where the camera is, which is always valuable, I think. But when you're interpreting that, it's important, I think. Yeah.
I also wondered if from your presentation, class size or grouping sizes or number of adults to children, at least maybe in K through 6, if those would be low-hanging fruit.
Yeah, so Susan, that's a wonderful example, because counting is a hard problem, much harder than you think. And it doesn't seem like it should be, because it's just counting, right? Like, again, I have a 3-year-old, she counts up to 12, then she skips 13, she goes to 14. But like, she's pretty good. and it can be hard. And she's kind of like little blocks on the floor. She counts. She doesn't make a mistake these days. But like, why is it so hard to count things with computer vision? And I don't have a good answer for why. But so what I've noticed is that so counting. So there's a problem called VQA in computer vision, visual question answering. And they had things like how many bananas are in this image? How many cars are in this image? Basically, every method learned to answer 2 because that was the prior distribution over data samples, and it didn't actually learn to count anything. So it was kind of like a no-op. It just didn't do anything. Then we had some work on, or I'm aware of some work on like bottom-up counting, which would mean like detect what you want to detect and then count, right? But our detectors are good, but they're not good enough to do that robustly. So if you're looking for like coarse binning, like it's a sparse room or a medium room or a crowded room, then you can probably get pretty high fidelity as long as you have the boundaries of those things. You'll never have some, like if sparse is 2 to 4 and medium is 5 to 10, then hopefully you never have someone with 4 to 6, some room, because at the boundary you'll always have that noise. But I just I'm not sure if it's wise to talk about because we just took it down, but we used to have a website at Voxel 51 called PDI for COVID. It was stood for Physical Distancing Index, and this would basically it connected to webcams, did human detection, and then reported the counting basically of the image frame, and then smoothed it over time. And it was exactly that notion of bottom-up counting. It used state-of-the-art method from Google, actually, something called efficient det. We noticed that when the scenes were dense, it undercounted, and when the scenes were sparse, it overcounted. There was just this systematic bias toward what it was counting. But it still was a reasonable signal to show you trends. So if trends are important, then you could use this idea. But if concrete, like specific 8 versus 9, I would be a little cautious still. Yeah. There was another question from a Michael about 51, who to contact for 51. I guess the easiest thing would be just email me. I'll put it into the chat, and I can give you pointers to where to go for how to get access to it and use it. It's all open source and free, so it should be straightforward. You can install it just by like pip install, or you can go to GitHub and get the code and build it and like work with it on your own. Any other questions? We're 5 minutes over, but I'm glad to see the interest. That's good. All right. Well, I think this has been wonderful. Thank you to my co-panelists here. Hopefully everyone has a good evening, and I look forward to talking more about these really great questions in the future.
And Jason, I just want to add, if you look in the chat, James put in the link if you want to go to the MIDAS social, which I believe is where we have been abandoned by some people to go to. So.
Right, I do see that link in the chat. So for everyone to join, indeed, that started 6 minutes ago now. So please go there if you're looking to chat a little bit more. Yeah. All right, thank you.
Bye.
Bye.